G'day and welcome to Agresol's Soil Organic Carbon Masterclass. This is the first part in a multi-part series where we deep dive into soil organic carbon and soil organic matter. Why is it so important? How we can build it? What it is in general, which is actually what we'll be talking about today. But really, this course or masterclass is to just get more information out there and clarify a lot of information to growers and farmers, anyone interested as to what soil organic carbon actually is. And so I've done countless of hours putting this all together, multiple drafts, doing a lot of research, aggregating all of this together. So hopefully you'll have a better idea of what's going on and the actual ways to build soil organic carbon. Again, this course is absolutely free. You can access the course either by YouTube or our website at www.agresol.com.au. There's no email opt-ins at all, so you can just go straight to our website and start viewing the content, or you can go to the YouTube channel and look through the playlist. There should be a soil organic carbon playlist. Again, completely free. The only ask I have of you is if you do enjoy this and you get a lot of benefit out of the content, that you just share with a friend. There's a share button on YouTube or on our website, share the link. It'd be great to get some of this information out there. Awesome, so let's get into it. So before we start talking about soil organic carbon and soil organic matter, let's talk about what is soil. Like when we talk about soil, what are we actually talking about? And so all soil starts as rock. So either this can be volcanic rock, so a volcano erupts and magma or lava flows everywhere. That forms into rock. It can be that kind of rock. It can be metamorphic rock, which is rock that's under pressure for a long period of time and crystallizes and then come to the surface with different geological processes. Or it could be sedimentary rock. So sandstone, sand's compressed over time and then has come up again. But everything starts off as parent rock, or all soil starts off as parent rock. Over time, these rocks will weather down. And so that can either be physical weathering, which is the rocks are actually getting smashed together and breaking up like that. It could be chemical weathering. This could be things like slightly acidic rain, which then causes acidic reaction with the rock and weathers that down. Or it could be a biological weathering of the rock as well, with different microbes, plants producing acids or physically breaking up that rock. And so over time, over lots and lots of years, this big rock will start to turn into smaller rocks until we get left with the actual soil particles. So our clay, silt and sand. But if we stop there and we just have broken down rock, that's all we have. It's just broken down rock. It's not soil yet. So soil itself has the weathered down rock material as well as organic components in it. So it has to have both for it to be soil. And that's what we have here. So we have our soil particles, but then with biology, we have our soil particles as well as these little red bits here are used to represent soil organic carbon. We have a plant root through it, fungal hyphae, or holding it together in little aggregates. You can see a really good photo here about a really nice soil profile on, should be the left-hand side is basically a conventional soil. You'll see at the very top there that that's almost like the plough layer, and in a very normal conventional soil, that's really where a lot of soil organic carbon accumulates. On the right hand side though is basically a regenerative farm, and you can see soil organic carbon has built all the way through the soil profile, and there's aggregation, there's really nice aggregation, roots throughout the whole thing, high amounts of soil organic carbon throughout the whole soil profile. So that is soil. It's weathered rock plus organic matter. And so when we think of, I guess, the whole soil profile and everything that's made of, there's an air component and a water component. Both of these is called the pore space. The amount of water versus air can vary depending on the amount of rain you've had or how moist the soil is. If you are basically in a drought, we're going to have more air than water. And if we're flooded, more water than air. Typically, soil has about 45% mineral content, which is our actual rock, and 5% soil organic matter component. This varies as well, depending on your location, depending on your climate, your farming practices, the type of minerals that are in our soil, and whether or not we're doing any practices to really burn off that soil organic matter. So now that we understand a little bit more about soil and what our soil is built up of, now we can actually start talking about soil organic matter. So soil organic matter is simply decomposed material that was once living. So if we think of plants, if we think of animals, microbes, anything that was once living, decomposed in our soil. And that is soil organic matter. Thanks for coming to the course. But we can take a step further and go, what components make up the soil organic matter? And there's 5 components here. So there's dissolved organic matter, which is root exudates effectively, which is sugars, amino acids, anything that dissolves in water. This makes up a very, very small amount of our overall soil organic matter. So of the 5% of our soil, only 5% of that is dissolved organic matter. But this is highly active in our soil. Microbes use this as a very quick food source for them to grow. Very important. This is what plants use to build that really nice rhizosphere around the plant root. So, dissolved organic matter. Then we have living organisms. These are microbes, so bacteria, fungi, nematodes, protozoa, anything really living in our soil. It's not quite earthworms. It has to be micro, so very, very small. Next, we have fresh residue. This is effectively plant material, animal material, that started to decompose, so things like leaf litter, old roots that are attached from the plant. It could also be livestock manure. So all those things are fresh residue. Now, when we have the combination of our living organisms and our fresh residue is called particulate organic matter. This is quite active. You can still see a distinct structure to this organic matter, and so you can identify what it is. But when we combine that with dissolved organic matter, we get labile carbon. Labile carbon is available for our microbes to use for development and growth, as well as to duplicate, so grow. It's very important that we have a labile carbon component within our soil for our microbes to grow. If we didn't, then they won't be growing. Now, our labile carbon is quite variable in a lot of soils, and it really depends on our farming practices. The more we have is a really good sign that we're building soil organic carbon. So if you can see that you're building labile carbon, it's a good chance that that is a leading indicator that you're building, or it's a prerequisite for building soil organic carbon on the more stable side. It's also important to know that this won't stay in our soil forever. So this needs to get converted into a different source in order for it to stay there. But regardless, it's still very important that we have this here. Next, we have humus. Humus is the main part that we'll be focusing on in the whole series. It is truly the component of soil organic matter that we get most of our benefits from. It's both stable and active at the same time. So we get all these benefits. It's highly beneficial to our soil, has so many characteristics, and it makes up 60% of our overall soil organic matter. So this is the thing we're trying to aim for, not so much the other things, although these flow into this. It's the humus, that's our end result. And so we'll talk about this in a bit more detail later on in this video. Finally, we have our resistant organic matter, makes up 15% of our soil organic matter. And this is really the last stage in a piece of organic matter's journey after being decomposed. It is the most inert, so it's not active at all. It's highly stable, very hard to build over time. So these are things like biochar would fall into this, completely decomposed material, and charcoal. So if we'd have like a fire, for example, a cool burn, and it builds up charcoal, that would be resilient organic matter. It's very inert, doesn't really do much. It's very important for structure building, but in total, our humus is a lot more important. So as I was talking about before, turnover, effectively our dissolved organic matter has the fastest turnover. It's super easy to be used by our microbes. It's only in our soil for days, minutes to days, very quick turnover, which means we need to be replacing this every day for our plants, which is so important to have roots in our soil all the time throughout the whole year. When we don't have dissolved organic matter, simply our living organisms won't have food for them to survive on, or at least our symbiotic microbes won't. Our saprophytics will, because they'll be eating our fresh residue. But things like mycorrhizal fungi that form symbiotic relationships with our plants won't have food. So it's very important to ensure that our dissolved organic matter is getting replaced. Anyways, turnover, minutes to days. It's also quite the newest organic matter. Next we have particulate organic matter, which is both a living and fresh residue. These are things that you'd get from a green manure crop or a cover crop, your stubble after harvesting wheat or your other cereals, or say for example livestock manure. That all comes into particulate organic matter, and this typically has a turnover between 2 to 50 years. Now ideally it'd be really good if we have biology and that can turn over a lot faster, so definitely sooner than 2 years, but some of the more tough things like I guess hardwoods or whatever can decompose up to 50 years. So it really depends on the type of matter that we're breaking down. If it has a high carbon component, it's going to take longer to break down. A high nitrogen component, it's going to take a shorter amount of time to break down. Next is humus. Humus, again, quite inert, so it's going to be in our soils for a longer time, tens to hundreds of years. But again, it is still quite active, so it has high CEC, high water holding capacity. We'll talk about this in the next video in the series, the benefits of humus, soil organic carbon in general. So that lasts for a bit longer than our particulate organic matter. Finally, we have our resistant organic matter. This is going to last from hundreds to thousands of years. Very stable in our soil, but not as active as our humus. So that's a quite general breakdown of soil organic matter. If we want to talk about soil organic carbon, which is I guess why we're all here, it's simply just the carbon component of soil organic matter. So if we think of glucose, for example, so this is glucose. Glucose is C6H12O6, so there's 6 parts carbon, 12 parts hydrogen, and then 6 parts oxygen. If this whole thing is soil organic matter, so if that is in our soil and soil organic matter, only this carbon is considered in the mass of our soil organic matter. So typically it's about 58% of our soil organic matter is soil organic carbon. And so the reason why we measure soil organic carbon and not so much soil organic matter is because it's just easy to measure in a lab. We can look at just the total amount of carbon in a sample and go, okay, that's our soil organic carbon, and then you can track it back to soil organic matter. So if you want to find out how much soil organic matter you have from soil organic carbon, you can divide your soil organic carbon by 58% or 0.58%. And if you want to find out how much soil organic carbon you have from soil organic matter, you can divide soil organic matter, you can times soil organic matter by 58%. There's the math. So another thing that I want to touch on is what is not considered soil organic carbon, and these are inorganic things in our soil that have carbon in it. So for example, calcium carbonate, which is Ca for calcium, C for carbon, O for oxygen, and there's 3 lots of those. So this is effectively lime in our soil. If you have this in your soil, it does not mean that you have soil organic carbon. This is not considered soil organic carbon because it did not come from something that was once living. It has to come from something that was once living. So now onto humus. Humus makes up between 60 to 75% of the overall soil organic matter. And ultimately, it's very hard to know what humus actually is. It's very difficult to research because it's not a defined compound. It's a chain, it's a complex of different carbon-containing compounds. And that's exactly what we've got here. So it's a brown to black complex of variable carbon-containing compounds. It is very difficult to know actually what it is, and it's very difficult to study because of that. It is made by mycorrhizal fungi by converting our root exudates into these really long, complex chains of carbon. It's not just carbon, it contains a whole bunch of different minerals that the mycorrhizal fungi pick up and attach to these chains. Now remember, our root exudates are also soluble organic matter. Typically, the mycorrhizal fungi will actually bond into the root of our plants, And so the root exudates won't so much go into the soil, but go straight into the mycorrhizal fungi to then produce humus. So when we talk about humus, humus can actually be broken up into 3 different groups. And each of these different groups are characterized by their solubility in water. So first we have humans. Now these are our largest compounds. You can see the photo here, very big. You'll be able to see human compared to glucose there. Glucose is quite small, even though it's a pretty big compound. It's actually quite small compared to human. So it's not soluble at all. It's a very, very large molecule. So in the order of 10 million to 100,000 grams per mole. These are massive molecules. Now, they're also the most stable out of all our humic substances. And for this reason, they make up a really important structural component of our soil organic matter, make up very important structural parts of our soil aggregates, and they add to this aggregate stability of our soil. For this, they have a very important role in our water holding capacity and improving our water holding capacity. And again, they improve our soil stability. So out of all our humic substances, these are also our most resistant to decay, either microbially or by oxidation. So these are the most stable, most structural. Think of these as very large scaffolding of our humic substances. Next, we have humic acid. Now, humic acid is any humic substance that is soluble in any water solution with a pH greater than 2. So everything except super acidic solutions. It's the middle size compound out of all of our humic substances. In terms of its size and mass, it's between 100,000 and 10,000 grams per mole. And because it's slightly smaller than humans, its reactivity or chemical activity is a bit greater. So it has a strong ability to bind to clays, making really strong aggregates. It also has a really interesting function with binding to different trace minerals and metals, making them more available for our plants to absorb. And therefore it increases the mineral uptake of these trace minerals. In fact, it can actually bond with over 60 different minerals for our plant to then use. So overall, humic acid has a really important function in binding to these clays, as well as its ion exchange, because it can bond with both cations and anions. And it has an important function in metal chelation. So when I talk about this chelation and being chemically active, what I mean by is its ability is for the compound's ability to have sites of positive and negative charge. So these components of our compounds have a slightly negative charge to them. So the oxygen, my understanding is that oxygen pulls the electrons towards it more, so it has a bit more of a negative component. The alcohol group has this hydrogen typically dissolves off, making the oxygen a lot more negative. And then we also have the combination of the two here. So as you can see in the overall molecule, it should be there, you'll see a lot of different sites on that. So each of those sites will be able to bond with a different trace mineral, as long as it's positive, and there should be some positive sites on the compound, which will allow it to bond with anions, so negatively charged compounds. So when we think of all that, fulvic acid actually has twice the ability to bond with different metals or trace minerals, has twice the ionic exchange as humic acid. So talking about fulvic acid, it's always soluble. It's the most soluble out of all of them. It's soluble regardless of pH. It's also the shortest. It has a mass or size of 10,000 to 1,000 grams per mole. So it's very small compared to our 100 million grams per mole, 10 million grams per mole there. It is so small that it's actually able to enter into our plant roots and our leaves. So it can actually go into our plants. The amazing thing that fulvic acid can do is actually carry trace minerals with it as it enters into the plant. And so for this reason, it's really useful for improving the efficiency of our foliar sprays. So adding a fulvic acid to our foliar sprays can increase its efficiency, meaning you get more bang for your buck when applying them. Similar to the fulvic acid, does have high amounts of those slightly negative or positive sites that it can bond with our trace minerals. When it does bond with our trace minerals, it actually turns into a humate. So humates are when our humic acid or fulvic acid bonds to a metal or really any mineral. So these can be iron, copper, zinc, calcium can work because it's a cation, as well as magnesium and manganese. And when it does bond to that, either in the soil or in a foliar spray, it increases its ability to be absorbed by the plant, and it's called chelation. And this is how it works. So the oxygen part of the molecule is a slightly bit more negative. So when it comes into close contact with a ion, it is really drawn close together, similar to like a magnet. Positive attracts the negative, or north attracts the south. They form a weak bond together. So a similar thing can happen with our alcohol group as well. And so this really increases the efficiency of the uptake of these metals and minerals, and it's really important for the functioning of our plants. Likewise, humic acid can actually also be taken up by the plant itself and used in different processes that we'll talk about in the next video of the series. So there you go, that's the humic substances. As you can see here, they vary in a fair amount of size and weight, all compared to our glucose molecule there. Now, when we consider the humic substances to all the other organic substances that can be involved in soil organic carbon, we have all our fats, all our lipids, we have our oils, we have charcoal, waxes, proteins or amino acids, we have our carbohydrates, cellulose, starch, all these different things that make up the overall thing of soil organic matter, but it's only these that make up humus. Awesome, well that's it for the first video of the series. If you're on YouTube, make sure to subscribe so you can see some of our other videos. Again, the only ask I have of you is to share with someone that you know would really appreciate this. Make sure to watch the next video in the series. We'll be talking all about the benefits that we get from soil organic carbon, and they are quite amazing. So make sure to tune into that. Otherwise, if you're a farmer in New South Wales, we do offer consulting services. So if you want help integrating some stuff that improves your humus content in your soil, either keep watching, it's for free, no opt-in, it's great, or get in contact with us and we can help you with that. Awesome. My name is Tilda Simmons. Cheers.